Hi AP Stats Scholars. For this lesson, we're going to talk about the last section of Unit 2, where we're analyzing departures from linearity. In previous lessons, we talked about what to do if our data is linear. We perform regression analysis. We get a correlation coefficient that gives us the strength of that linear relationship. And then we use regression analysis to get a linear model or least squares regression line to help us make predictions. We also talked about what happens when our data is curved, so there is a pattern but not linear. And that's what we're going to talk about today. First, we're going to go back to that idea of unusual points. So when we're looking at linear relationships, typically unusual points are going to fall in one of three categories. The no unusual points obviously is its own category, so this is the ideal. We don't have any data points that deviate from that pattern. And then the other three cases are we have a data point that's far from the rest of the data set, but it still follows that linear pattern. We have a data point that is far from the rest of the data set, but it doesn't lie along that line. Or we have a data point that's far from the rest of the data set in the y direction, but doesn't follow that original line. In both cases, I see an effect on that least squares regression line. So originally in these first two pictures where we either don't have an unusual or our unusual meets the pattern, we can see that that least squares regression line is 3 plus 0.65x. Looking at the case where we have a value that's far in the x direction, our line, instead of tilting upwards, now tilts downwards. And that's changed both the y-intercept and the slope. In picture 4, where our unusual point differs in the y direction, the slope is almost the same or the same, and it's the y-intercept that's been affected. We've effectively picked up our line and shifted it upwards from where it was before. So generally, when our influential point is far from the data in the x direction, it's going to affect both pieces of that equation. When it's in the y direction, we typically see a change in the y-intercept, but a much smaller, if any, change in the slope. And if it's in the same pattern, we shouldn't see much, if any, change at all to our regression line. There's some new vocabulary that we need to talk about with regards to unusual points. First, points with high leverage are points in regression that have much larger or much smaller x values than other points in the data set. Outliers, when we talk about linear regression, are a point that does not follow the pattern of the data and has a large residual. And an influential point is any point that, if removed, substantially changes the slope, y-intercept, correlation, coefficient of determination, or standard deviation of the residuals. Outliers and high leverage points are typically influential in regression calculations. Words are hard today. if we go back and look at those previous pictures, high leverage points have much larger or much smaller x values. So looking at cases 2, 3, and 4, this point here has a much larger x value. So I would classify this point as high leverage, and this point here has a much larger x value. So I would classify this point as high leverage. An outlier is a point that does not follow the pattern of the data and has a large residual. So in this picture here, this point follows the original pattern. So he's got almost no residual. So even though he's a high leverage point, he's not really having much of an effect on my linear regression line. So I would not call him an outlier. Cases 3 and 4, on the other hand, I can see that this guy has a large vertical distance from the original line. This guy also would have a large vertical distance from that original best fit line. Both of these would qualify as outliers. And if we look at the values in that box, here was our original data set. Notice that in all 3 of those boxes, we have changes to the correlation coefficient, we have changes to the standard deviation, we have changes to the coefficient of determination, and in cases 3 and 4, we also see changes to the y-intercept and the slope of a regression line. So 2, 3, and 4 would qualify as influential points. So both outliers and high leverage are usually influential. So let's go ahead and do an example together. This one says, to compute property taxes in Pennsylvania, the state assigns a value to each house called the assessed value. Here is a scatter plot of the assessed value of a house in dollars and the living space in square feet for a sample of houses in Pittsburgh. The least squares regression line has been added to the scatter plot. Describe how the point representing house A affects the equation of the least squares regression line, correlation, coefficient of determination, and standard deviation of the residuals. Is the point an outlier or a high leverage point? Explain your reasoning. So looking at this graph, the first thing I'm going to do is mark kind of the middle of the graph. So we expect that the average is somewhere around here, middle of the picture. And looking at where house A is, notice that house A has a less than average living space. So he's on the lower end of the line, and he sits below the line. That point is going to stay fixed, and what this point does is he causes rotation on the line this way, pulling this end down, tilting that end up. So that's going to have an effect on both the slope and the y-intercept. If I'm tilting this end down, that's going to make this end a little bit lower. So the first thing that's going to change is my y-intercept is going to get closer to 0. And the other thing that's going to happen is as this line rotates a little bit, that's going to increase the tilt, and we know increasing the tilt increases the slope. And both of these things are happening because point A is less than the average living space. And because it is below the line. It does follow the linear pattern of the rest of the points. It's pretty close to that line. It has a very small residual compared to our already existing least squares regression line. And since it follows the pattern of the rest of the data, we expect that it's going to strengthen that linear relationship. And if it's going to strengthen the linear relationship, both r and r squared should get closer to 1. The last thing we were asked to look at is the standard deviation of the residuals. And because this new point, house A, is close to the line, it has a small residual, it's going to decrease the standard deviation of the residuals. Part B asks us to do the same thing if we add house B to our analysis. I'm going to pause the video, give you a second to do that. I'd like you to talk to your neighbors if you can, and then we'll come back and take a look at the solutions for house B. So looking at point B in our picture, point B is pretty close to that mean living space and is significantly above our original least squares regression line. And remember that for points that don't follow the pattern, not close to the line, doesn't match that overall linear, and have a large residual, we classify them as outliers. So point B is an outlier. For the y-intercept and the slope, because he's so close to the mean, he's not going to cause a lot of tilt like point A did. So we're not going to see a large change in the slope, but he is going to pull the whole line up towards him. So our y-intercept is going to increase as the whole line shifts upward, but that slope shouldn't change much. Because he's an outlier, he is going to decrease the strength of that linear relationship, and so both r and r squared are going to get closer to 0. Because he's so far above the line, house B's residual is going to be large, and that's going to increase the overall standard deviation of our residuals. On the AP test, you should be able to determine the effect that adding a new point to your data set will have on the regression analysis for that data set. So y-intercept and slope, r squared and r, and the standard deviation of the residuals. The next thing we need to talk about is what do we do if our data is curvilinear or nonlinear? And the answer is we can transform one or both of the variables to make the scatter plot linear. And then we can use regression analysis on that transformed data. This is something that I think is easier to see if we do an example first. So we're going to do an example with a type or a set of data, and then we'll come back and talk about how those transformations work. So for this example, we have a set of data that's looking at the number of bacteria present in a petri dish in thousands after a certain amount of time. So for example, after 1 hour, there's 1,800 bacteria in the Petri dish. And we're asked to create a scatter plot and a residual plot. And we're not going to do this by hand because we remember that we can do this using our calculator. So stat, edit, and we're going to put this data into a list. And that's enough to create a scatter plot, but I also know I want a residual plot, and in order to get the residuals in memory, I need to run linreg. So we're going to go stat, calc, option 8, and we want to run that on list 1, list 2. And I need to set up my calculator because I have not done that yet. It's the frowny face. There we go, that looks better. Looking at that regression analysis, I can see that my correlation coefficient is fairly strong. That rounds to 0.96, that's almost 1. I'm expecting a strong linear graph. Let's go ahead and take a look at that stat plot. So stat plot, I want my scatter plot on, scatter plot list 1 and list 2. Then to graph, we go zoom, and we want zoom stat, option 9. Ooh, and you can see I have some data here. Let's clear that. So I'm going to go ahead and sketch that really quick. Reminders that when you do a quick sketch from your calculator, you still need to label everything. So this represents hours, because that's my explanatory. I know X is always the first column, Y is the second. And then this is number of bacteria in thousands. And how many data points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 data points. So our graph looks something like this. I think I messed up here a little bit. Definitely did, but we're going to notice. I know that my smallest hour is 1, my biggest hour is 5. I know that down here my smallest number is 1.8. I know my biggest number here at the top is 18. So I want to make sure that that scale matches what I'm seeing here so that we have some idea of shape. And looking at that scatter plot, I mean, definitely increasing, but that does not look linear. That looks curved. Frowny face. We know we create a residual plot to check, so we're going to go back to stat plot, and we're going to change that y-list to resid. And to pull up resid, remember we go to our list menu, second, stat, and I want option 8, which is resid, and then zoom stat. and I get an interesting shape here. Again, I need to label. I plotted hours on the X, and I plotted my residuals on the Y. And I can see 2 data points above on either side, and then the rest of the data points kind of forming a curve below. And that clearly forms a pattern. And remember, with residual plot, if our data is linear, this should be random scatter, and it's not. So the parent function in our scatter plot, if I look at that shape, that looks like exponential growth to me. And those of you who've taken AP Bio know that bacteria in a dish will exhibit exponential growth up to some point where they start to compete for resources and can't grow like that anymore. So this looks like an exponential curve. And I know that to undo those exponential curves, I want to use a logarithmic function. Logarithms undo exponentials. And we're doing this because our scatter plot is not random scatter. Not scatter plot, sorry, residual plot is not random scatter. So for exponentials and logarithms, the most common types you're going to see are base 10 and base E, which is the natural base, which means logarithms would either be base 10 logs or the natural log, base E. You can do some trial and error to test whether base 10 or base E works better. Because I set up this problem, I happen to know that base E, the natural log, would be the best way to transform the data. On the AP exam, if you need to do this by hand, they are going to tell you the transformation. So the AP board isn't completely evil. If you were working through this by hand, they would tell you which transformation to perform. Here, we're doing a natural log to undo that exponential growth that we see. So what we've done is we've taken a natural log of our y value. So x, y, natural log of y. And now we're going to create a scatter plot of x versus natural log of y. So let's go ahead and go back to our data. The data here is rounded. I'm super lazy, and I know I can put equations in my calculator. So I'm going to put natural log of list 2 here and have the calculator do it. And you can see I get unrounded values. And now I want to create a scatter plot of x versus ln of y. So I'm going to go back to stat plot, and I'm going to change my y list to list 3. Oh, and that looks so nice. That looks almost perfectly linear. Ooh, and I'm not going to write ln of y. I'm going to write ln of number. And then hours. again, I'm providing some idea of scale, so those axes have meaning. And then I'm going to check my residual plot. And I already kind of have an idea of what I should see, but we should still check. So our residual plot is going to be hours on the x, our explanatory, and then resid on the y. And in order to get a residual plot, I need to rerun linreg on list 1 and list 3. So stat calc option 8, and I want to rerun it on the transformed y list. I can see my correlation coefficient went up. It's much closer to 1. That's a good sign. And now let's do that residual plot. So second stat, and I'm going to choose my resid from the list, and then to graph it, zoom stat. And that looks a lot more like random scatter. So this is a better model for linear regression because our resid plot shows random scatter. To find the regression equation, we're going to go back to linreg. So stat calc option 8, and again we're running it on x versus natural log of y. And so I get my y-intercept is negative 0.0047. My slope is 0.5860. And when I write this, remember that I took the natural log of y hat. So I have to include that in my equation. Now that I have my linear model, I can predict the number of bacteria in the petri dish given a time. And this problem says, using the equation above, find the predicted quantity of bacteria after 3.75 hours. And you'll notice, before I do the math, that input value, hours, is in this range. So I'm not doing extrapolation. This is reasonable input given the data that I collected. And we're doing the same thing that we did for predictions last time. We're going to take that x value and we're going to substitute it into our equation where we saw x. So natural log of y hat equals negative 0.0047 plus 0.5860 times 3.75. And we're going to go ahead and do that on our calculator. And I get 2.1928. And I'm not done. remember that I want the quantity of bacteria, I want number. And right now, on the left, I have natural log of the number. So I have to go back to Math 3 knowledge, and I know that I undo natural logs by raising them to a base, turning them into an exponential expression. So I'm going to make both of these exponents on base e. And when I do that, the exponential base e undoes the natural log. And so what I get is that y hat equals e to the 2.1928 power. And that's something we can do on our calculator. Above natural log, I see e to the x, so second natural log, 2.1928. And we get 8 point, and I'm going to round this to 1 decimal place because that's what was in my table originally. So, let's round it to 2, 1.96. That rounds nicely. And if I go back to my table, 3.75 is between 3.5 and 4, and 8.96 is between 8.0 and 10.6. So that matches the pattern of the original data that we saw, which is good news. If this were the AP exam, I should then write a sentence. So we expect there to be 8,960, because remember that number was in thousands, bacteria after 3.75 hours. In this example, you'll notice two things happened. First, I had to guess a transformation and apply it to one of my lists. In this case, we transform the y, because I clearly recognize this pattern is exponential, and I know to undo that exponential curve, I want to take a log. And taking a log of the y value turned this into a roughly linear graph. So I had to choose the correct transformation here, and then when I made my prediction, I had to undo that transformation by turning it back into an exponential. So on the test, you need to know the relationship between the original data and the transformed data. So for base 10 exponential, I know I want to take a log base 10. If my original function was squared, I want to take a square root. I have to know the connection between the original and its inverse function. So there are a couple of things that we want to keep in mind as we choose models. As I mentioned, it's very unlikely that you're going to be asked to do this by hand. Most of the time, the AP test will tell you what model to use if they want you to do this. But if you were asked to do this by hand, two things you want to keep in mind. First, as you're testing different models to see which gives you the best fit, you want to choose the model, whose residual plot has the most random scatter. Because we know random scatter in a residual plot is generally a good indicator that our linear model is a good model. If more than one model produces random scattered residual plots, we want to choose the model that results in the largest coefficient of determination. And that's easy to check because we know when we go to make our residual plots, we run linreg, and one of the outputs of that linreg command is r squared. So if we keep track of our r squared as we're making our residual plots, it'll be easiest to pick out the residual plot with the most random scatter and the highest r squared. There are a couple of common patterns you're going to see on the exam. So the first is when it's a slight curve, clearly not linear, but not a strong curve, and it passes through 0, 0 or very close to 0, 0. That transformation is usually natural log x, natural log y. So you're going to need to transform both list 1 and list 2. If you see a stronger curve and it appears to be exponential, that's what we just saw. This graph clearly looks exponential. We just transformed the y. If the graph looks like a square root graph, so it starts at 0, 0 and it goes this way, we're going to do square root of x. If it contains 0, 0 and it appears logarithmic, meaning sharp increase and then flat, as opposed to a much shallower increase, that's natural log of the input, natural log of x. Most of the transformations you're going to see on the test are exponentials and logarithms, or squares and square roots. So if you've got those two relationships down, you should be good. Alright, if you have any questions on what you saw in the video, feel free to send me an email. Otherwise, I'll be back on campus on Wednesday and you can drop by room 101 with questions. I'll see you on Wednesday.